And we're live. So I know we're a little bit short on people today. I think it's because the AP exams are running a little bit late, so we've got people who are testing upwards of 4 in the morning. Might still be asleep, but we'll put out a recording for them. So I'm going to quickly review all of our limits and continuity stuff. I'll mark out all the stuff that's not on the final exam from our cheat sheet, and leave you guys with a bunch of former quizzes to study from and the homework. So starting off with continuity, continuous, removable, or non-removable are all you need to know for this class, so we don't need to know the different types of non-removable discontinuities by name. However, you'll still need to be able to recognize all of these as a non-removable discontinuities. These are subcategories of non-removable discontinuity that we'll need to work on for Calculus 1 or 2 next year. For a function to be continuous, it must have a general limit, and that general limit must be equal to the point. So has a general limit, which means the limit from the left and the right are the same. And the general limit is the same y value as when you plug in the point. Okay, so here our limit from the left and the right is 4, and when you plug in the point you actually get 4, so this is continuous. Okay, for removable discontinuity, you have a general limit, but the general limit's not the same as what happens when you plug it in. So here both sides are approaching a y value of 2, but when you actually try to plug in 2, I've got a white dot here, which means we're undefined. Could also be something like this, where both sides are approaching a general limit of y equals 5. But when you actually plug in the points, we get a y value of 2. For non-removable discontinuity, the left's limit does not equal the right limit or any of the one-sided limits approach infinity. So here I've got our one-sided limit is approaching negative infinity from the left. Our one-sided limit approaches positive infinity from the right. Those are not the same, so this is not have a general limit, and they're infinity. So for both of those reasons, this is a non-removable discontinuity. Here, my limit from the left is 4, my limit from the right is negative 2. So I don't have a general limit, so this is a non-removable discontinuity. Same thing here. Limit from the left is not the same as the limit from the right. And here, there is no limit from the left, and there is a limit from the right, which means my general limit does not exist. Okay, so let's try a couple of these. Okay, so I'm going to ask for a limit from the left, right, and general. What happens when you plug it in? And then what's the continuity? Starting with, oh, we've got more people. Starting with Aileen. At the point A, what is my limit from the left? Okay, so I've got options. Everything is either 1 or 2. So at the point A, what's our limit from the left? Okay, 2. Limit from the right? Also 2. General limit? 2. And what happens if I plug in the point? 2. Okay, so everything is 2 for point A. So is this continuous, removable, or non-removable? Continuous, perfect. Okay, so at point B, Kelly, what's my limit from the left? Okay, limit from the right? 2. General limit? Okay, so right, does not exist. And what happens when I plug in the point? Does not exist, because both of these are white spaces, okay? Sarah, for C, what's my limit from the left? 2. And limit from the right? Okay, negative, say again? Negative infinity, perfect. What's my general limit then? Does not exist. And if I plug in the function? Also does not exist. Okay, perfect. Kenichi, can you see?
Yes.
Okay. At point D, what's my limit from the left?
0.
Limit from the right?
0.
In general?
0.
And when you plug it in?
0.
Okay. I need to go back so I wasn't defining these, but is point D continuous, removable, or non-removable?
Continuous.
Continuous, perfect. Sarah, for point C, was that continuous, removable, or non-removable? Non-removable, perfect. And for point B, Kelly, is that continuous, removable, or non-removable? Non-removable, okay. I'll look at one more. So point E, Aileen? It is non-removable. What happens when you try to plug in the point? So in this case, does not exist. So we don't have one point that, one y value that we would get when we plug this in. We've got a vertical asymptote at x equals e. So even though the limit from the left is infinity, the limit from the right is infinity, and so the general limit is infinity, we don't know that the y values are going to be the same y value. My limit from the left could be 200 at the point when my limit from the right is 300. It's still useful to know that both sides are approaching infinity, but there's no one point that we're approaching. When you plug in the point, we won't know where to go. Okay, any questions on continuity? Anything? Okay, I'm going to add one more thing for our continuity part, and that's differentiability. Now that we know how to derive. In order to be differentiable, we must be continuous, which means we have a general limit, and the general limit is equal to what happens when we plug in the point. And the limit as we approach the left side of our slope must equal the limit as we approach the right side of our slope. So notice we've got this extra derivative here. So we must be continuous. And approach the same slope from both sides. Okay, so as an example of a place where our function is continuous but not differentiable. So at this point, we are continuous because our limit from the left and from the right is the same as what happens when I actually plug in the point. But our slope is not approaching the same value. You can see there's a sharp edge here. So my slope was positive on the left side, but negative on the opposite side. And it wasn't smooth. It didn't approach zero from both sides first. It just kind of changed. So this is continuous but not differentiable. I can't derive this because our limit of the slope from the left and the right is not the same. At any other point on this function, we would be differentiable because all of the points in this function are continuous and our slope is approaching the same value from the left and the right. So taking a look at this, I'm on Kelly next. Kelly, am I differentiable at point A? No. Why am I not differentiable at point A? Perfect. We've got a sharp point, what we call a cusp, and that happens when your slope is different from the left and the right, without touching zero in between. Okay, Aileen, am I differentiable on point B? No, you're right. Why not? Because, say one more time, I'm sorry. We do have a slope as we approach the right side, so the slope from the right is approaching zero, the slope from the left is approaching zero. Change. This point is not continuous. And in order to be differentiable, we must be both continuous and approach the same slope from the left and the right. Let's do one more, Sarah. At point C, so that's at 0, am I differentiable? Okay, we are not differentiable. You're right. Why are we not differentiable? 2 reasons, actually. See if I can get both of these up at the same time. Okay, so why am I not differentiable at point C? Okay, so we've got 2 options. The slope could be different from both sides, or it could not be continuous. Either one of those would cause us to be not differentiable. Or both. At point C, am I continuous or not continuous? Okay, I think your microphone's cutting out because I can hear you saying something, but I'm not sure what. See, I'm gonna grab someone else really quick. I'm sorry. Aileen, can you help us out? Why is point C not differentiable? Aileen's muted. I'm going to open to anyone. So why is point C not differentiable? Okay, so for both reasons. We're not continuous. We don't have the same general limit, so we can't be continuous. And we're not approaching the same slope from both sides. From the left, our slope is 0. From the right, our slope is approaching positive infinity. So because our slope is not the same, it can't be differentiable, and because we're not continuous, we can't be differentiable. Okay, Kenichi, at point D, are we differentiable?
Yes.
Yes, you're right. We're differentiable because we are continuous, and our slope from the left and the right is both approaching the same value.
Yes.
Awesome. Yeah, just erased our line. There we go. Okay, any questions on differentiability? All right, I'm going to move a little bit faster through our old stuff. I have several different methods of solving limits analytically that you guys can check out if you need to. I have one new part for El Hospital's rule. This is a shortcut that you can use if you know how to derive that I didn't teach you in quarter 1 because we didn't know how to derive yet. So the shortcut is if you end up with a function that is a fraction, so you have a numerator and a denominator, and when you try to take the limit, you end up with either zero over 0 or plus or minus infinity over infinity. Then you can take the limit as x approaches a of the derivative of the numerator divided by the derivative of the denominator, and the limit will be the same as the original function. So what that means is, first be careful because this is not quotient rule. We're deriving the top separately from the bottom. But what that means is if you tried to take the limit of a function like this, sine x over x, when you first plug in 0, what would I get? Who am I on? We just did Kenichi and Sarah. I'm going to jump back to Kelly. Kelly, what's the sign at 0? And if I plug in 0 for x, I get 0. So this is 0 over 0. So that means we can use El Hospital's rule. So if I take the limit as x approaches 0 of the derivative, Sarah, what's the derivative of sine? Cosine. So this is the cosine. What's the derivative of x? One. Okay. So this is cosine x over 1. And if I plug in 0, I'll get the cosine at 0, which is 1 over 1. Okay, so I could say because we got 0 over 0, El Hospital's rule applies, which means the limit as x approaches 0 of the sine x over x should be equal to 1. Since that's the limit as x approaches 0 of the derivative of the numerator divided by the derivative of the denominator. Okay, this can shortcut through a lot of the extra factoring problems that you had earlier. A lot of the limits by rationalization could be solved this way. You don't have to know it for your final, but you can save time if you can use it. Squeeze theorem is not on your final exam. Limits at vertical asymptotes, I've got examples that I've sent through the WeChat, so I'm not going to focus on that right now. But I do want to talk about limits at infinity. So if we're approaching infinity and you have polynomials for your fraction, then if your largest power is on top, you'll approach positive or negative infinity depending on the sign. If your largest power is on bottom, we'll approach 0. And if your powers are the same, you'll approach the fraction of the coefficients. So that's the fraction of the numbers that are in front. In this case, 3 over 2. If you don't have a polynomial, then we can follow these rules to see which side grows the fastest. Factorials grow faster than exponentials, grow faster than polynomials, grow faster than logarithms, grow faster than sine or constant, grow faster than constants. So for instance, I've got a factorial divided by a logarithm because factorials grow faster than logarithms. I've got my largest power, if you want to think of it that way, on top, my fastest growth rate on top, which means we should approach positive or negative infinity depending on the sign. And if I plug in positive infinity, my natural logarithm will become positive as I approach infinity, and my factorial is also positive, so this is positive infinity. For my second example, if I plug in infinity right now, I've got polynomials on top and an exponential on bottom. Because exponentials grow faster than polynomials, my bottom will grow faster than the top as I approach infinity, which means our limit is 0. And the last one, I've got logarithms and constants on both sides. Logarithms grow faster than constants, so I only care about this part. With the power property of logarithms, I can move the 7 and the 5 down. So that leaves me with the same growth rate, ln x, on top and bottom. So I'm going to take the fraction of my coefficients, which is 7/5. And that's my limit. Any questions on any of the 3 examples? Okay. I'm going to check our randomly generated sheet here to see if we've got anything we could use El Hospital's rule for, and then we'll take a look at that. Potentially. Okay, either one of these I believe would work. Yeah. So 7 or 8. Okay, for number 7, we could sit here, factor, and then cancel. If you couldn't figure out how to factor this, though, we could cheat with El Hospital's rule. When I plug in -3, I'll get 9 plus 3 minus 12 is 0. And -3 plus 3 is also 0. So I've got 0 over 0, and we can use El Hospital's rule, which says this limit should be equal to the same limit if I take the derivative of the top divided by the derivative of the bottom. Aileen, what happens if I derive the top?
Derive
Yep. I want you to derive just the numerator.
2x cubed over 3 minus
Oh, that's integrating, I think.
2x times x.
So this will be multiply by the power, decrease the power by 1. So this is 2x to the first power for the first term.
And then minus 1.
Minus 1. Okay, and then I've got this negative on the outside. I'm going to leave it on the outside. Okay, and then what happens when I derive the bottom? 1. Okay, so I'm going to take the limit as x approaches -3. So I can just plug in -3 right now. So this is -2 times -3 minus 1. 2 times -3 is -6 minus 1 is -7 times -1 is +7 is my limit. We can check. If I wanted to solve this one using our normal factoring method, the limit as x approaches -3 of x minus x squared minus x minus 12 would factor into x minus 4 and x plus 3 over x plus 3. My x plus 3's will cancel, so I'm left with negative x minus 4. If I plug in -3 for x, I'll end up with -7 or 7. So I realize this particular problem would probably be faster to factor than it would be to use El Hospital's rule, but if you get stuck on your factoring and you're not sure you're not sure which factors should work, or if you've got maybe a third order, or fourth order, or fifth order polynomial that's going to take forever to factor, you can shortcut with El Hospital's rule instead. Okay, Kelly, next one. If I plug in 0 right now, what would I get on top?
1 minus sine pi over 2.
Okay, what's the sign at pi over 2?
1.
1. So this is 1 minus 1 or 0 over 0, which says I can use El Hospital's rule. So what happens if I derive the numerator?
Negative cosine pi over 0 plus x.
Okay, divided by
Divide by 1.
by 1. Okay, I'm not deriving the whole fraction. I'm deriving the numerator separately from the denominator, so we don't have to worry about quotient rule. And when I plug in 0, what's the cosine at pi over 2?
It's negative cosine pi over 2 with 0.
0. So our limit is equal to 0. Okay. That should be it for today. On WeChat, I've given you several different examples from previous quizzes. They do take a minute to load. So you can see you won't see anything when you first load this. Just wait for a couple minutes, for a couple seconds rather, and the work should pop up. It's kind of a lot to load at once. There we go. So these are the previous quizzes that we took in quarter 1 with all of the answers, my own steps, so step-by-step work, and my rubric, so how I graded you last time. The format's going to be pretty much identical on your final exam. And then for homework, we've got 10 practice problems on limits, which for this class I'll be looking for by Thursday at midnight. And that should be it for today. If you've got questions, feel free to stick around. If not, then I'll see you guys on Thursday. Thank you very much for coming. Goodbye.